Hello everyone, my name's Iman. Welcome back to my YouTube channel. In today's lecture, we're going to examine some key experiments that collectively demonstrate the wave-particle duality of light and matter. These experiments include blackbody radiation, the photoelectric effect, the emission spectrum of hydrogen, and the double slit experiment. Together, these findings provide evidence for light's particle-like behavior through quantized photons and its wave-like properties through interference patterns. We're also going to discuss the Rydberg equation, which explains the quantized energy levels in hydrogen spectral lines, and we will go over de Broglie's equation, which extended wave-particle duality to matter. Let's start with a review. In our last special topics lecture, we introduced photons as quantized energy packets. Quantized means that energy comes in discrete, fixed amounts rather than existing as a continuous flow. We also talked about how the energy of a photon is directly related to its frequency and inversely related to its wavelength, and how photons can be categorized across the electromagnetic spectrum based on these properties. On this note, we also mentioned that photons exhibit both particle-like and wave-like behavior. But how do we know this duality exists? This understanding comes from a series of really important experiments that were done in the early 20th century. And again, they include blackbody radiation, the photoelectric effect, the emission spectrum of hydrogen, and the double slit experiment. We're going to start today by talking about blackbody radiation. So, what is a black body? A black body is an idealized object that absorbs all electromagnetic radiation that falls on it. None of it is reflected, none is transmitted. Because of this, it's often used as a theoretical model to study how objects emit radiation. What makes a black body special is that it emits radiation solely based on its temperature. The type and intensity of radiation it emits doesn't depend on its material, and it doesn't depend on surface properties, only its temperature. For instance, when you heat a piece of metal, it starts glowing red, then orange, and eventually white as the temperature increases. A black body behaves in a similar way, but it represents the ideal case where the emission is purely temperature-driven. Now, classical physics attempted to explain black body radiation with the Rayleigh-Jeans law. This is an equation that calculates the intensity of radiation as a function of frequency. According to this law, a black body should emit radiation at all frequencies, and the intensity of radiation should increase continuously with frequency. However, there was a significant problem with this prediction. As the frequency increases into the ultraviolet region, the Rayleigh-Jeans law predicted that the intensity of emitted radiation would become infinite. In other words, the black body would emit an unlimited amount of energy at high frequencies, which is physically not possible. And this inconsistency became known as the ultraviolet catastrophe. The resolution came from Max Planck, who proposed this revolutionary idea. And he said, energy is not continuous. Instead, it's quantized. He suggested that electromagnetic energy is emitted in discrete packets called quanta or photons. The energy of each packet is going to be proportional to its frequency, and it can be calculated using this equation right here. Energy is equal to Planck's constant multiplied by frequency. This is also equal to Planck's constant multiplied by the speed of light divided by the wavelength. We saw this equation in our first special topics lecture. This experiment was super important because it solidified that energy is not continuous but quantized. Keep that in mind as we move into the second experiment, the photoelectric effect. The photoelectric effect refers to the process by which electrons are emitted from the surface of a metal when light shines on it. At the time, classical wave theory suggested two main ideas about this process. The first idea was that the energy of the ejected electrons should depend on the intensity of the light, regardless of its frequency. And the second main point is that light of any frequency should eventually eject electrons as long as the intensity of the light is high enough. Intensity here, by the way, refers to the brightness of the light, or more specifically, the amount of energy being delivered to the metal per unit area per second. Classical physics assumed that increasing the intensity of the light should increase the energy of the ejected electrons. However, these predictions were proven incorrect through careful experiments on the photoelectric effect. And here's what the experiments actually demonstrated. Point 1. No electrons are emitted if the frequency of the light is below a certain threshold, no matter how intense the light is. In other words, the energy of the light must meet a specific minimum frequency for the electrons to be ejected. The second point is, once the threshold frequency is exceeded, increasing the intensity of the light increases the number of ejected electrons, but it does not affect their energy. And the third point is that the energy of the ejected electrons depends only on the frequency of the light, not its intensity. And to explain these results, Einstein expanded on Planck's idea of quantized energy. He proposed that light is made up of particles or photons, and that the energy of each photon is proportional to its frequency. For an electron to be ejected, the photon must carry enough energy to overcome the work function of the metal, and the work function of the metal is the minimum energy required to remove an electron. If the photon's energy exceeds the work function, then the excess energy is transferred to the ejected electron as kinetic energy. This relationship is described by the following equation. This equation describes how the energy of an incoming photon is used to overcome the work function of a metal, with any excess energy being transferred as the kinetic energy of the ejected electron. So consider a metal with a specific work function. This is the minimum energy required to eject an electron from its surface. Now imagine we shine a photon of light on this metal, and this photon of light has a specific energy. If the energy of the photon exceeds the work function, then the electron of this metal is going to be ejected. The electron gets ejected, and that ejected electron is going to have a kinetic energy that's equal to the difference between the photon's energy and the work function of the metal. And that is the photoelectric effect. Now we can move into our third experiment and discuss the emission spectrum of hydrogen. In the early models of the atom, electrons were thought to orbit the nucleus much like planets orbit the sun, And this orbit is maintained through a balance between the attractive Coulomb force and the centrifugal force that's generated by the electron's motion. However, this model had a significant flaw. Electrons, they carry a charge, and it's well known that any charged particle undergoing acceleration emits electromagnetic radiation. This radiation causes the electron to lose energy continuously. And if this were true, the electron would gradually lose energy, and then it would spiral inward and eventually collapse into the nucleus. And that would render atoms unstable and incapable of existing in the form that we observe. In addition, as the electron radiates energy continuously, classical physics predicted that light would be emitted across all possible wavelengths, and that would produce a continuous spectrum. However, experiments demonstrated that this prediction was incorrect. When hydrogen gas is energized, it emits light. And when that light is passed through a prism to analyze the wavelengths that are being emitted, the result is not a continuous spectrum. Instead, the light splits into a series of discrete spectral lines, each corresponding to a specific wavelength of light. And this is known as the emission spectrum of hydrogen. These distinct lines revealed that the energy emitted by electrons is not continuous, but instead it's quantized, meaning electrons release energy in fixed amounts. To explain this phenomenon, Niels Bohr proposed a revolutionary model of the atom. He suggested that electrons exist in quantized energy levels, meaning they can only occupy specific orbits around the nucleus, each associated with a defined amount of energy. Electrons, they could not exist in between these levels. And this idea solved the problem of atomic stability. As long as an electron remains in one of these energy levels, it does not emit energy. Bohr's model also explained how electrons move between these energy levels. To transition from one level to another, an electron must absorb or emit a specific amount of energy. When an electron transitions from a higher energy level to a lower one, it releases energy in the form of a photon. And the energy of the photon corresponds exactly to the difference between the two energy levels. This energy determines the photon's wavelength, and it can be calculated using this equation right here. The wavelength of the emitted light is equal to Planck's constant multiplied by the speed of light, and that is divided by the energy of the photon. So in summary, the emission spectrum of hydrogen demonstrated that electrons in atoms occupy specific, quantized energy levels. Let's break this down further to fully understand what's happening. When electrons interact with light, two processes can occur. We can have absorption or we can have emission. In the absorption process, an incoming photon is absorbed by an electron, giving it the energy needed to move from a lower energy level to a higher one. This is how an electron becomes excited. On the other hand, during emission, an electron that is in a higher energy level releases energy as it drops back down to a lower level, and it emits a photon in the process. When we observe these processes, we see two types of spectra. We have our absorption spectrum. This occurs when electrons absorb photons to move to a higher energy level. When we observe the absorption process, the spectrum is going to look like a continuous band of colors with certain dark lines interrupting it. The absorption spectrum shows through those dark lines the specific energies of photons that are actually absorbed by an electron in an atom. These photons have just the right amount of energy to match the exact difference between two energy levels in the atom, and that allows the electron to become excited and move to a higher energy level. Then we can look at an emission spectrum. This occurs when electrons release photons as they drop to a lower energy level. So here we see bright lines of specific wavelengths against a dark background. So the emission spectrum shows through the bright lines the specific energies of photons that are emitted by electrons in an atom. These photons are released when electrons jump from a higher energy level back to a lower one, and their energy corresponds exactly to the difference between those two energy levels. Each spectral line, whether it's an absorption spectrum or an emission spectrum, corresponds to a transition between two specific energy levels. And these transitions are governed by the difference in energy between the initial and final levels. We can now explore these spectral lines in more detail. These lines are grouped into series depending on the final energy level of the electron after it transitions. The Lyman series consists of transitions where electrons fall from higher energy levels down to the first energy level. These transitions release high energy photons and produce lines in the ultraviolet region of the spectrum. The Balmer series includes transitions where electrons drop from higher energy levels to the second energy level. These transitions release photons in the visible region of the spectrum. The Paschen series involves transitions where electrons fall from higher energy levels to the third energy level, and these transitions emit lower energy photons, which produce lines in the infrared region of the spectrum. The energy of the photon emitted during these transitions is directly related to the difference in energy between the two levels, and this can be calculated using the Rydberg equation that you see here. In this equation, E is the energy of the photon emitted. This is equal to R, which is the Rydberg constant. This is equal to 2.18 times 10 to the minus 18 joules for hydrogen. This is multiplied by 1 divided by NL squared, where NL is the lower energy level, minus 1 divided by NH squared, where NH is the higher energy level. This equation allows us to calculate the exact energy difference for any transition, which can then be used to determine the wavelength of the light emitted, for example. Also, an important point here is that as we move to higher energy orbitals, going from 1 to 2, from 2 to 3, from 3 to 4, the energy difference between consecutive levels becomes smaller and smaller, meaning it takes a lot more energy to transition from n equals 1 to n equals 2 than it does to transition from n equals 9 to n equals 10. So to summarize this part, electrons can only transition between quantized energy levels, and they need to either emit or absorb photons in the process. The energy of the photon corresponds to the exact energy difference between these levels. And finally, these transitions result in distinct spectral lines, which we can observe in both emission and absorption spectra, and that gives us a lot of important information about the atom. We can now discuss our last and final experiment, the double slit experiment. When a beam of electrons is directed through two narrow slits onto a screen, something really cool happens. Instead of forming two distinct patterns like you would expect if electrons were just behaving like particles, the electrons instead create an interference pattern. This is a series of alternating bright and dark bands. This pattern can only be explained if the electrons are behaving as waves, with the bright bands representing constructive interference and the dark bands representing destructive interference. This demonstrates that electrons and particles in general exhibit wave-like behavior under certain conditions. So, what does this mean in the broader context of what we've learned? Each of the experiments we've discussed contributes to our understanding of the wave-particle duality. Blackbody radiation and the photoelectric effect reveal the particle-like nature of light through the concept of photons and quantized energy. The hydrogen emission spectrum shows that electrons in atoms also exhibit quantized energy behavior. And the double slit experiment demonstrates the wave-like nature of particles like electrons through interference patterns. So together, these experiments provide strong evidence for the wave-particle duality. Now, I want to make this especially clear. Matter, just like light, exhibits wave-like behavior. This phenomenon, known as wave-particle duality, it applies to both light and matter. And de Broglie really explored this concept, and he introduced the idea of a matter wave that's described by this equation. This equation says the wavelength is equal to Planck's constant divided by mass times velocity. Mass times velocity is equal to momentum, so we can alternatively write this as Planck's constant divided by momentum. This equation demonstrated that any particle with mass and velocity has an associated wavelength, although for larger objects, this wavelength is so small that it's practically undetectable. But for particles like electrons, the wavelength is significant enough to calculate and observe. From this point, I want to state that while de Broglie's equation opened the door to understanding matter waves, it also highlighted a limitation in Bohr's model of the atom. Bohr's model worked really well for hydrogen. It explained the quantized energy levels and the emission spectrum for hydrogen, but it did fundamentally treat electrons as particles moving in fixed orbits. This approach was ultimately incorrect. Modern quantum mechanics replaced Bohr's fixed orbits with the concept of orbitals. So unlike orbits, which imply defined paths, orbitals are regions of space around the nucleus where there is a high probability of finding an electron. And this probability view of electron behavior accounts for both the particle-like and the wave-like nature of electrons, and it aligns with the principles of wave-particle duality. Orbitals will be something we discuss in great detail in the next special topics lecture. For now, let's go ahead and tackle some practice problems. This first problem says, which of the following statements is or true about the photoelectric effect? Statement 1 says, the sum of the work function and kinetic energy of an ejected electron is proportional to the frequency of incident light. This statement is true. Earlier, we saw the photoelectric equation. It told us that the kinetic energy of the ejected electron is equal to the energy of the incident photon minus the work function of the metal. If we rearrange this equation, we see that the energy of the incident photon is equal to the sum of the work function and the kinetic energy of the ejected electron. And therefore, we can say that is proportional to the frequency of incident light. So just to rephrase, according to Einstein's explanation of the photoelectric effect, the energy of an incoming photon is used to overcome the work function. Any excess energy is converted into the kinetic energy of the ejected electron. Thus, the total energy depends on the frequency of the incident light. Statement 2 says, given light of high enough intensity, electron can be ejected from any surface. This statement is false. The photoelectric effect depends on the frequency of the light, not its intensity. If the frequency is below the threshold frequency of the material, then no electrons are ejected regardless of the light's intensity. Intensity just affects the number of photons, but not whether ejection occurs. So again, intensity affects the number of photons and thus the number of electrons ejected, but not whether ejection occurs. So statement 1 is true, statement 2 is false. What about statement 3? Statement 3 says, Einstein employed the concept that photons have quantized amounts of energy to explain the effect. This statement is true. Einstein introduced the idea that light consists of quantized packets of energy called photons, and he used this concept to explain how photons transfer their energy to electrons, leading to ejection when that photon's energy exceeds the work function. So statements 1 and 3 are true, making the correct answer for problem 1, answer choice E. Let's move on to problem 2. Problem 2 says, for a Bohr atom, which of the following transitions emits the highest energy photon? A says from n equals 10 to n equals 9. B says from n equals 4 to n equals 3. C says from n equals 6 to n equals 5. And D says from n equals 2 to n equals 1. In the Bohr model, the energy levels of an atom are quantized, and the spacing between these levels decreases as n increases. The correct answer here is going to be D, from n equals 2 to n equals 1, because the energy levels near the nucleus are farther apart than those at higher n values. As a result, the transition from n equals 2 to n equal 1 involves a much larger energy difference than any of the other options, and therefore it's going to emit the highest energy photon. Problem 3 says, which of the following emission lines corresponds to part of the Balmer series in the spectrum of a hydrogen atom? The Balmer series includes transitions where electrons fall from a higher energy level to the second energy level. Now, looking at these options, the correct answer is going to be B, from n equals 4 to n equals 2. Because this transition is from a higher energy level, n equals 4, to the second energy level. And that is the definition of the Balmer series. Now, problem 4, our last and final problem, says, according to de Broglie, which of the following objects has the smallest wavelength? A says electrons, B says neutrons, C says protons, and D says molecules. De Broglie's equation states that wavelength is equal to Planck's constant divided by mass times velocity. And this equation shows us that the wavelength of an object is inversely proportional to its mass. So objects with greater mass will have smaller wavelengths. Among the options that are provided, D molecules have the largest mass, resulting in the smallest wavelength. So the correct answer for problem 4 is D. And with that, we have completed this lecture. I hope that this was helpful. Please let me know if you have any questions, comments, concerns down below. Other than that, good luck, happy studying, and have a beautiful, beautiful day.